Letzten Schritt im Promotionsverfahren von Herrn Samer-Darwig, Master of Science. Und es gibt ein paar Verfahrensschritte, die ich jetzt hier nach einer wunderschönen Handreichung des Kollegen Lamke Schritt für Schritt durchführen werde mit ihm. Ich informiere Sie kurz darüber, wie das Ganze abläuft. Also, Herr Darwig hat eine Dissertation eingereicht mit dem Titel, den Sie dort schon sehen, in englischer Sprache: Corrosion Protection Concepts for Aluminium and Magnesium Alloys coated with silicate films prepared by water-based salt-gate process. Und für die primär deutschsprachigen, unter Ihnen gibt es eine deutsche Version, Konzepte für den Korrosionsschutz von Aluminium- und Magnesiumlegierungen mittels Sohlgel-Prozess hergestellten Silikatfilm auf Wasserbasis. Ja, für diese Dissertationsschrift hat es 2 Gutachten gegeben. Die liegen der Fakultät natürlich seit geraumer Zeit vor. Man hat dort festgestellt, dass das Verfahren fortgeführt werden soll, deswegen sind wir heute hier. Vorhin hat das Rigorosum stattgefunden, also die Befragung durch die Gutachter, durch mich als Vorsitzender der Kommissionskommission, und wir sind wieder zu dem Schluss gekommen, dass das Verfahren fortgesetzt werden kann. Jetzt werden wir also gleich hören einen Vortrag in 30-minütiger Länge. Dann werden wir noch die Gelegenheit haben, Fragen zu stellen, sowohl die Gutachter als auch Sie als Zuhörende. Bevor es dazu kommt, möchte ich Ihnen ganz kurz die Promotionskommission vorstellen. Da haben wir auf der einen Seite zur Linken den Kollegen Thomas Landke, Professor Oberflächentechnik, Funktionswerkstoffe, hier vom IWW und Doktorvater, verantwortlich maßgeblich für die Betreuung dieser Doktorarbeit. Und auf der anderen Seite den Kollegen Professor Heinrich Lang von der Professur Anorganische Chemie aus der Fakultät für Naturwissenschaften. Protokollant heute ist der Herr Zillmann von uns vom IWW. Ich selbst bin als Vorsitzender der Promotionskommission Martin Wagner, Inhaber der Professur Werkstofftechnik am IWW. Bevor Herr Darwig jetzt die Gelegenheit bekommt, seinen Vortrag zu halten, darf ich Ihnen ganz kurz vorstellen. Ich habe also hier einen Lebenslauf gefunden von Ihnen, dann ist es auch eingereicht worden. Herr Darwig ist geboren in Syrien, in Aleppo. Steht auf dem Titelblatt, steht es drauf. Und er ist dort auch zur Universität gegangen, hat Chemie studiert, hat einen Bachelor und einen Master of Science dort erhalten, ist dann seit geraumer Zeit in Chemnitz als wissenschaftlicher Mitarbeiter tätig gewesen und hat dort seine Promotion verfasst von Kollegen Lamke. Und Sie sind mittlerweile in Schwäbisch Gmünd, ja, in einer Forschungseinrichtung oder einer Firma von Forschungs. Okay, ich denke, das soll an dieser Stelle genügen. Jetzt habe ich Sie furchtbar lange stehen lassen. Bitte nehmen Sie Platz, ich werde mich dazusetzen und wir freuen uns auf den Vortrag. Herr Darwig.
Thank you very much. Dear officers, thank you very much for coming here today. The topic of my presentation is corrosion protection concepts for aluminium and magnesium alloys coated with silicate films prepared by water-based solvent process. In this presentation, I would like to discuss an introduction about solvent process and the application of silicate films, objectives of the work. In the experimental part, I would like to talk about cost-efficient silicate films, crack-free silicate films, self-healing and long-term corrosion protection, sealing of the ceramic coatings in the soil, and the soil geology process is defined as the formation of an oxide network through polycondensation reaction in the soil. And the soil is a solid, is colloidal suspension particles. The size of these particles is in the range of nanometers. The gel is a 3-dimensional network which is formed from polycondensation of the particles in the soil. Usually, the soil is prepared from organometallic materials, deionized water, and related organic compound, ethanol or methanol, in order to achieve dispersion of the organic materials with water and to obtain a homogeneous solution. Also, catalyst is added to the soil in order to accelerate the hydrolysis reaction. Several factors can affect the solvent process, like chemistry of the soil, aging period, and pH value. The chemistry of the soil, there is a hydrolysis and condensation reaction. In the hydrolysis reaction, hydroxyl group is replaced by OH, and reaction, there is two kinds. Alcohol condensation reaction or water condensation reaction. In both cases, the monomer can be turned to dye. The second factor can affect salt gel process is aging period. Usually aging period is carried out 3 or 4 days. During this period, there is hydrolysis and condensation reaction take place. The monomer turned to dimer and then particles. The size of the particle can be increased to a few hundred nanometer or a few micrometer. It depends on the aging period, a few days, months, or more. Third factor can affect on the salt gel process is the kind of catalyst. In the case of acid catalyst, the polymer is linear, and the silicate films prepared by acid catalyst are dense and has important protection. In the case of base conditions, clusters are formed and there is a pause between these clusters. And so therefore, silicate films prepared by base conditions, it has no protection. Several products can be obtained by salt gel process. It depends on the further treatment of the solid, like aerogel, monolith, fibers, nanoparticles, and coating, which is the topic of this presentation. Silicate films prepared by salt gel process has an advantage and disadvantages. In the case of advantage, it has high purity film materials, low processing temperature, it is between 100 and 150. The salt gel process is less toxic than chromatic process, which is an advantage. The homogeneity of silicate film and mild chemical conditions. pH value of the solution is about 4.535, so therefore it is mild conditions. Disadvantage. The high cost of the starting materials. Volatile organic compounds are needed to achieve the homogeneity of the solid. These materials are toxic like methanol, flammable, and it also has a cost. Cracking are usually formed in the silicate film during the heat treatment, and these cracks are the main reason for corrosion. Also, thin films only can be applied, thickness maximum 3 micrometer. When the film thickness 4 or 5 micrometer, that's mean cracks will occur. After the advantage of silicate film, I would like to mention the objectives. The objectives of this work are preparing of cost-efficient protective silicate films, which can be achieved by water-based solid and using a cost-efficient starting materials, crack-free silicate films, through nanoparticles stored in the film, self-healing. Two main points will be discussed in the case of self-healing: evaluating the long-term corrosion protection and reducing the quick leg of corrosion inhibitors from the silicate film. And also improving the corrosion protection of the ceramic coatings during the sealing process in the soil. The volatile organic compounds are usually added to the soil to achieve homogeneity, mixing between organic materials and water. When low hydrophobic saline materials are used to prepare the solid, like TOS and GBTM, these materials can be accepted as a low hydrophobic material when compared with silanes carbon 18 or 20. Alcohols, which are produced by the hydrolysis reaction of alkoxy group, are sufficient to achieve the homogeneity of the solid. So that means no need to use volatile organic compound. And so therefore the solution is called water-based solid. The silicate films prepared in this work by the following steps: silanes with deionized water and hydrochloric acid as a catalyst. The mixture is aged 3 days at room temperature. During the aging period, hydrolysis and condensation reaction take place. Monomer turned to dimer and then particles. After 3 days, the film was applied on the aluminum and magnesium substrate by heat coating. The cross-linking of the silicate film was carried out by heat treatment, 3 hours at temperature 100. After this heat treatment, a cross-linked film can be formed on aluminum or magnesium substrate. Different concentrations from the soil were tested. 6%, which prepared from this ratio, GBTM, TOS, and water. The scanning electron microscope for the surface of this film showed that this film is not completely covered the surface. Here is the metal, aluminum, and here is the silica layer. So therefore, the samples coated in this film has no protection, no corrosion protection, and has no barrier property and no stability in chloride solution. Other concentrations were tested, 20, 30%, and at 50%, which is prepared by this ratio, has the best corrosion protection. It's clear here from the scanning electron microscope for the surface of the sample. The film is completely covered the surface, and the samples coated with this film has much better protection than these samples. Also, this film suffers cracks, and these cracks are formed during the heat treatment. During the heat treatment, there is an evaporation of water. We are working in water-based soil, and traces of alcohols which are produced by the hydrolysis reaction. Also, there is a shrink age in the film, reduction in the volume of the film. At the same time, the film is connected with the substrate, so therefore, at the end, cracks are formed in the film. And these cracks are the main reason for corrosion. Corrosion solution penetrating the cracks and corrosion starts. This point was solved by using nanoparticles. The nanoparticles stocked in the silicate film has two main advantages. Number one, it improves the volume of the film, thickness, much better. Here can be seen the scanning into microscope for the cross-section of silicate film without nanoparticles. Thickness is about 3 micrometer until 4 micrometer. And in the case of film with nanoparticles, thickness improved until 8 micrometer. So that means the nanoparticles here behave as a filling materials in order to improve thickness. The second advantage of the nanoparticles is the crack-free film. This is in the case of film without nanoparticles, that's the cracks. And in the case of film with nanoparticles, no cracks can be detected by scanning electron microscope, which can be explained that the nanoparticles produces shrink age in the film and less stress, internal stress in the film, so therefore less cracks. The second topic is self-healing. Self-healing is defined as ability of the material to heal damage automatically without an external intervention. It's self-healing is going on in our human body. When the skin is wounded, after 3 days it will be healed. The same process will be applied on the metal. Here is corrosion inhibitor stocked in the silicate film, and this film was deposited on aluminum or magnesium substrate. When a defect appears in the film, is a defect area, corrosive solution penetrates in the defect area, reach the substrate, and the corrosion starts. Also, corrosive solution penetrates in the structure of the film. The corrosion inhibitors leach out of the film to the defect area to form a layer. This layer can be called corrosion inhibitor layer or self-healing layer, which prevent the effect of the corrosive solution. Different factors can affect solvent process, like structure of the film, the ability of the corrosion inhibitors to leach out of the film, the ability of the corrosion inhibitors to form a layer, a parallel layer in the defect area, and other factors. Different corrosion inhibitors were tested in this work. Here we have a list of these chemicals. And the most effective corrosion inhibitors were cerium nitrate and benzotriazole. Self-healing mechanism of these corrosion inhibitors can be explained as well. In the case of cerium nitrate, corrosive solution penetrates in the defect, corrosion inhibitors leach out, and the cerium ions in the defect area can react with hydroxide ions generated by cathodic corrosion reaction to form cerium oxide. Cerium oxide has a low solubility in aqueous media. That means it will precipitate in the defect to form a layer. Also, benzotriazole leach out of the film to the defect area and absorb on the metal, aluminum or magnesium substrate in the defect in order to improve the barrier property of the self-healing layer. The size of the defect in the film is an important factor to evaluate the self-healing. In this work, the size of the defect was chosen to be 10,000 micrometer length, and the width is 150 micrometer. which is 600 times bigger than what usually used to evaluate the self-healing. And the idea here is to test the ability of this coating to heal macro-sized defect in convergent resistance. Scanning electron microscope for the surface of the defect showed this is the silica film, and this is the defect area, and the aluminum substrate is uncoated. After 700 hours in a solution 0.5 mole sodium chloride. In the case of sample without corrosion inhibitors, the scratch area is completely destroyed, pitting corrosion can be seen, depth of the pitting corrosion can reach to about 40 micrometers. In the case of corrosion inhibitors, a layer of corrosion inhibitors or self-healing layer is formed in the defect, which prevent the effect of the corrosive solution on the metal substrate. Also, it can be seen here that the cracks at the scratch edge also healed. It looks like when the skin is molded and healed. The electro characterization showed that when cerium nitrate and benzotriazole docked in the silica film, two corrosion inhibitors, the aluminum sample coated with this film has much better protection than in the case of one corrosion inhibitor. This line is U1. The imbalance here is much better than when one corrosion inhibitor is used. This behavior can be explained by the cerium nitrate form a layer, which is cerium oxide layer in the defect area, and then benzotriazole also leach out of the film to improve the barrier property of this layer. So therefore, two corrosion inhibitors can give more protection than one corrosion inhibitor. And the long-term corrosion protection in this board was evaluated by means of self-healing efficiency. The electrochemical characterization showed that the self-healing efficiency is stable during emerging period, always stable between emerging period 100 and 700 hours. This is the sample with corrosion inhibitors, in comparison to the sample without corrosion inhibitors. Almost the stability of the self-healing efficiency can be explained by means of the development of the barrier property in the defect area. And this can be achieve 2 points. Number one, reducing the penetration of the corrosive solution to the defect area, better protection, in order to reach the long-term corrosion protection, and also reduces the leaching of the corrosion inhibitors out of the film. So therefore, it can reduce the weak rate of corrosion inhibitors, because the corrosive solution will not penetrate more in the structure of the film. By other words, long-term corrosion protection and reducing the lack of the corrosion inhibitors can be achieved by improving the barrier property of the layer in the defect, which can be reached by using cerium nitrate and benzotriazole together, mixture of corrosion inhibitors. In the case of magnesium, the electrochemical characterization showed that the samples with corrosion inhibitors has much better corrosion protection than the samples without corrosion inhibitors. In the case of after 100 hours emerging period in chloride solution, the film with corrosion inhibitors showed 100 times corrosion protection better than without the corrosion inhibitors. Now, sealing of ceramic coatings in the soil. In the case of anodized aluminum, the main reason for corrosion for anodized aluminum is the pores. The corrosive solution penetrates the pores, reach the substrate, and the corrosion stops. Different sealing methods are usually used. I would like to discuss sealing in the soil here. The cross-section of the anodized aluminum sealed in the soil, water-based soil, showed that if silicate film can be formed on the annex layer, silicate film thickness is about 4 micrometers. It's well known that anodized aluminum has a low stability in sodium hydroxide solution. Here is anodized aluminum and unsealed after 12 hours in 0.5 sodium hydroxide. It's clear that the static area is completely destroyed. And after the sealing, after 12 hours in sodium hydroxide, there is no traces of corrosion or oxide dissolution. This can be explained by the silicate film on the annex layer behaves as a barrier layer which prevents the effect of sodium hydroxide on anodized aluminum. Also, the plasma anodizing of magnesium, pores and cracks are distributed all over the surface. This is before sealing, and after sealing it's completely covered. The cross-section of this sample shows the cracks and the pores can reach to the substrate surface, as here. And after the sealing, all these pores and cracks are filled with silicate film. The substrate test showed that this is the magnesium sample uncoated. The plasma anodized magnesium, there is a traces of corrosion, that's clear. And the plasma anodized magnesium sealed in the soil, there is no traces of corrosion. Also at the corners, here the corners are covered because of the spray. Stability of the soil is an important factor to reach a cost-efficient process. The experiment showed that the soil at this composition, pH value 4.5, is stable more than 1 year in a closed container, of course, at room temperature. The conclusion? In the case of cost-efficient soil, the cost-efficient soil is achieved in this work by means of water-based soil and the cost-efficient starting materials. Cracks refilled. The cracks are usually formed during the heat treatment of the silicate film. The nanoparticles topped silicate film has two main advantages. Number one, it improves the film thickness, and number two, it reduces the film cracks. The cracks in the film because less shrinkage in the film. About self-healing, the size of the defect is an important factor to evaluate the self-healing process. Size of the defect in this work was chosen 600 times, bigger than what usually used in evaluating the self-healing. And coating is able to heal this film, this scratch area. The development in the barrier property in the self-healing layer in the defect was achieved by using a mixture of corrosion inhibitors, cerium nitrile and diazothiazole together. And this achieved 2 points. Number one, reducing the penetration of the corrosive solution in the defect area, that means less corrosion, in order to reach the long-term corrosion protection. Number two, it reduces the penetration of the corrosive solution in the structure of the film, that means reducing the lag of the corrosion inhibitors from the film. Sealing of ceramic coatings. In the case of anodized aluminum, a barrier silicate layer is formed on anodized aluminum, which improves the stability of this sample in sodium hydroxide solution, which is not the case of unsealed sample. In the case of plasma anodizing, the silicate film is formed in the pores and the defect of the layer, which improves the barrier property of this film and the stability of the film in the corrosive solution, magnesium chloride. The stability of the soil. A soil, water-based soil at this composition, pH value 4.5, showed stability more than 1 year at room temperature, of course, in closed container. At the end, I would like to thank Professor Lamke, my chef, and Professor Lang, Professor Wagner, my colleague. I would like to thank my colleagues in the Institute and Department of Electronic Politik, and Chemical Coating Technology with the staff and my colleague in the Institute, and thank you very much.
Das war ein schöner und kurz knackiger Vortrag. Sie haben also Ihre angekündigte Zeit unterbrochen. Wir haben damit Zeit für Fragen und wie die meisten von Ihnen wissen, beginnen die Gutachter. Wir haben vom ersten Gutachter an, Thomas. Thank you very much.
We just talked to each other because we're really happy to see that you draw your attention to the conclusions, that we really can see the benefit of your work. So, but coming to the concept, to the early beginning, when you started years ago, we were talking about the concept. And we all know sol-gel is not new, and we can look up hundreds, tons of papers dealing with sol-gel solutions on different ways. Could you please introduce again, roughly, what is your concept, and why or how could you find a way through all the preliminary works and establish a new concept for your approach for corrosion protection of different materials?
The work is experimental work is 110 days. 50% from the work about self-healing. And I have an idea from the self-healing. Usually, the self-healing matter literature, which I read already, it's just putting the corrosion inhibitors and it will leach out and form a line. And this is not my aim here. I have two corrosion inhibitors. Sorry, no. One is serum liquor, which has a relative high solubility in aqueous media, and benzotriazole, which has low solubility in aqueous media. And the idea is when the defect is formed in the layer, serum will not leach out and will be relative high concentration to form a layer, because there is a corrosion in the defect. I need a layer to short time. Serum will try to form this layer because it has high solubility, and serum oxide will form. And benzotriazole has low solubility in aqueous media, and it leach out of the film in low concentration. So that's when I reduce the rate of corrosion inhibitor because I need always corrosion on the layer. And the serum the benzotriazole improves the barrier product of this layer because serum oxide is formed already and it has defect. And I need to recover these defects in order to have barrier in the defect of the sample. And it can be achieved by using benzotriazole. Now, the first experiment showed it is attractive because of this photo here. Okay. Because it's sealed, I mean, it's completely clear that there is no corrosion in comparison with the sample. So that means the first experiment looks important, attractive, and this work can be developed later by using more than 1 to 2 corrosion inhibitors, maybe 4 or 5, but different solubility. This is my idea.
One of the main points also is to get rid of the wok. And instead of using wok, we use water. So, and as we know from water-based paints, water is beneficial because of environmental reasons, whatever. But when you put in solvents, water-based solvents, I mean, you have to get rid of all this water. And what we really can see is you have a lot of cracking. Yes. So if you look now in the light of water evaporation and cracking and all these problems and the input of energy to get rid of the water, how would you validate your concept?
Actually, it's still better than alcohol-based salt because of flammability and also the cost. And in the case of the cracks is not only from the water. I mean, the cracks is usually happening in the salt gel process, in the coatings, the films, because of the different spring age in the film. So that's mean the water is not the main reason for cracks. And I have a film thickness of 10 micrometer. I don't think it's for evaporation of water can be proper. Maybe it can make pores, but not big cracks.
Talking in volume percent, how much volume percent of water is in your layer? 50%. So if you get 50% off something,
The idea is 50% water, but heat treatment is not directly in the oven. There is a heat treatment at room temperature. I leave it 1 hour, maybe drying. So the layer is dry, most of water will evaporate, and then by heat treatment, it's crossed into the process. So that means not 50% from the water is evaporated during the heat treatment.
Just coming to the concept, in the proposal, we ask you about the passive, active, and temporary corrosion protection. What is this now?
It's passive.
You mentioned that there is an advantage for your coating concept because you have a high purity of the silicate film. Is that really needed, a high purity of that film?
No, it's not needed.
But you mentioned that.
It is the common advantage of silicate films. In some applications like microbiology, so they need the purity.
Making the salt active, we need the aging time.
Yes.
that, well, 3 days of aging time is fine, really the best. What gives you really, what indicates nicely prepared, aged sold solution? What kind of indicators do you have? Measures?
Yes, actually I tried different aging periods. 1 day, 3 days, 5 days, and also 2 days. Yeah. And after the aging period, I applied the coating on aluminum substrate and measured corrosion. This is the main parameter.
Let me give you an example. You have a co-worker working on the subject, and he comes back from holidays on Thursday and mixed all these soles. Then we get the weekend. And what's going on with that? Problem? Is it good to start later? Is it better to start on Friday before?
So later, starting later is better. Because,
but not for your business.
Of course.
I mean, therefore, I ask you, the efficiency of the aging time is important.
Yes.
How can you steer? How can you affect a short but nice, short aging time, but a nicely prepared soul?
You mean 3 days is long time?
It is.
Yes, there is one possibility to reduce pH value of the solution in order to reduce the process. But I used pH value 4.5 because I am working on aluminum. If I have a pH value less than 4, that's when the film will not be stable. I mean, aluminum oxide will be removed in the solid, and so therefore silica film will not be stable on the substrate. So therefore I am controlled by pH value 4.5. I can't make a lot of pH value.
Okay, I think that is a point we have to work on for future. Let me come to the tracking. We have been talking already about water evaporation. We have mentioned that. You talked about alcohol, and you said kind of shrinkage, alcohol. And there's again the shrinkage of your composition. That was not clear to me.
It was condensation of the molecules, the reaction, and during the condensation reaction there is evaporation of water, and so therefore the volume of the film, the size, dimensions will be less. Yeah. At the same time, you mean the reason of the reaction. At the same time, there is the film is connected to the substrate by covalent bond, which is strong bond. So therefore, at the end there is internal stress in the film and
okay. And to get rid a little bit of these internal stresses, you added nanoparticles.
Yes.
Why nano? And what really is the effect of that?
I'd like to raise something with you.
Fine.
Also, this is the film without nanoparticles here. Okay? When I take this size, the same size from 2 films, this is nanoparticles. Shrinkage here is more than here, because here in this area I have nanoparticles, which take part of this area, part of this volume. So therefore, shrinkage here will be less in this area, less than here. Change in the dimension will be less, and so therefore cracks will be less.
I mean, my question was directed to the sizes of the particles first.
Okay.
How thick is the layer?
About here, about 8 micrometers.
How much? 8 microns. So I mean, if you use 0.5 micrometer of the particles, it would also work.
It should be. But I use nanoparticles and I use ultrasonic in order to avoid agglomeration.
But the particles are
1500.
okay. But the character of the particle is ceramic. So by using ceramic particles, the cracking behavior of the entire concept, the entire layer,
I tried 3 kinds of
might be not
nanoparticles.
that beneficial.
I tried 3 kinds of nanoparticles: silicium dioxide, silicium carbide, and zirconium oxide. In all cases, there is a reduction in the cracks.
Yeah, okay, but I'm talking about the sensitivity to cracking. Did you try that? Did you apply bending stresses or not? Okay. You have to be honest. Okay. One question regarding to your self-healing and particles. We talked about particles. Do you try to identify active nanoparticles, how they could maybe contribute to the self-healing process?
In the case of silicium dioxide nanoparticles, I wrote a mechanism. There is possibility to formation of this ion, which can react with aluminum in order to form aluminum silicate layer. And this aluminum silicate layer looks like self-healing layer because it improves the barrier property of the silicate films and less corrosion.
This is where we can go in more detail in that. In fact, I have one question regarding the self-healing. You talked about leaching. Okay, leaching means something moves from some place to another place. We have migration, we have maybe diffusion, whatever we have. And then you fill the crack. Well, it's a crack. And it looks like in the middle over here. And now we step into the loop and we get a crack right besides the second crack.
Yes.
Is there enough material, is there enough inhibitor around so that we can prevent that area, that specific area, from